Okay, so what did we learn last time? We learned how to find out the coordination number and the oxidation number of a complex ion, right? So in this session, we're going to learn how to name a coordination compound. Okay, we do have some rules to follow, but it will be easy once you get to know the rules and how to do that. Okay. Naming coordination compounds, what do we know to do? The cation is named before the anion. Just like sodium chloride, we have sodium as the cation first and then the chloride. Similarly, coordination compounds also, we name the cation first and then the anion. And then within the complex ion, the ligands are named in alphabetical order before the metal ion. Okay, we first name the ligands in alphabetical order before the metal ion. Anionic ligands, if you have anionic ligand, we drop the "ide" and add "O" after the root name. Okay, for example, if you have a chloride as a ligand, which is an anionic ligand, chloride, Cl minus is chloride. So for anionic ligands, we drop the "ide" chloride and then we add chloro, CHLORIDE. You drop "ide" and then you add O. So chloride become chloro, okay, after the root name. A numerical prefix is used to indicate the number of ligands of a particular type. Prefixes do not affect the alphabetical order of ligand names. So the ligands are named in alphabetical order. So we can have prefixes like di, tri, tetrakis, or numbers, prefixes like that. But the prefixes doesn't affect the alphabetical order of the ligand names. Ligands that include a numerical prefix in the name use the prefixes such as bis. Bis is for 2. Tris is for 3 and tetrakis to indicate their number. And then a Roman numeral is used to indicate the oxidation state for a metal that can have more than one state. Normally we have oxidation states more than one for transition elements. So if it involves transition elements, we have to say the oxidation number of the metal. If the complex ion is an anion, okay, if you have a complex ion as anion, we drop the ending of the metal name and add 8. If it is aluminum, we would say aluminate. If it is chromium, we would say chromate. If it is a complex anion. Let's look at some examples. You will understand it a little bit more. So these are some names of some neutral and anionic ligands. So if you have water, that is being named as aqua. Ammonia, NH3, amine. That's the name of the ligand. This is carbon monoxide, not carbon monoxide, carbonyl group. It's called carbonyl, CO. And NO stands for nitrosyl. These are neutral ligands. And some of the anionic ligands, F minus, remember the fluoride will become fluoro. Chloro, bromo, iodo, hydroxocyano. Hydroxocyano, like that. Okay. Names of some metal ions in complex anions. Remember, if you have a complex anion, the name will end as 8, like aluminum, aluminate, chromium, chromate. So iron would make it ferrate, copper, cuprate, lead, plumbate, silver, argentate, gold, orate, tin, stannate, like that. Okay. Let's look at these examples. What is the systematic name of this complex? Okay, so what do we need to do first? So this here we have a complex anion, right? So you first always we first name the cation, which is sodium, right? So the complex ion is, it's a complex anion. Go back. No, I want the pen. Pen, there you go, thank you. Okay, sodium is a simple cation, and this guy is the anion, right? So what are the ligands we have? We have fluoride, but if it is a ligand it would be fluoro. So there are 6 fluoro groups. For 6 the prefix would be hexa. So then it would be hexa fluoro. If it is a complex anion, aluminum will end as aluminate. Hexafluoroaluminate. Aluminate is going to be the complex anion. So at the front we have sodium. So the correct answer would be therefore sodium hexafluoroaluminate. Okay. And then the next one. What is the systematic name for this one? Here let's see what do we have first. We have within square bracket and nitrate. So what do we have? Always we have is first we have cation and then the anion. So we have square brackets to begin with, meaning we have a complex cation and a simple anion. Simple anion is nitrate. Now we need, so this CO is cobalt. En stands for ethylene diamine. Ethylene diamine, En. And then there are 2 chlorines. So we have chloro, CHLORO. We have a chloro group and we have ethylene diamine. Okay. So ethylene diamine and chloro. So which one should go first? In the alphabetical order, C goes first, then the E. So then it should be chloro comes first, right? And then how many chloro groups are there? 2 chloro groups. So if there are 2, we call dichloro. For 2, dichloro. Ethylene diamine. Now for ethylene diamine, there is a di already there for ethylene diamine, but there are 2 of those. So to represent that, there are 2 of the ethylene diamine groups, excuse me, we have to put the prefix bis, B-I-S. Bis, 2, bis represent 2. Dichloro bis ethylene diamine, and CO stand for cobalt. Okay, cobalt, and cobalt is a transition element. So we need to figure out what is the oxidation number for the cobalt. So the transition element cobalt, and we figured out what's the complex cation, dichloro bis ethylene diamine cobalt. We now need to figure out what is going to be the oxidation number. Okay, so now this part is nitrate -1, so this whole thing is +1. So +1 is the complex cation, minus the charges of the ligands will give us the charge of the metal ion. Ethylene diamine is a neutral ligand, so there is no charge for that. And chloro group, chloro is -2. Because there are 2 chloride groups. Each chloride is -1, so there are 2, so it's -2, right? So +1 +2 makes it +3. So cobalt is then oxidation number +3. So then your answer is going to be first you have to write the name of the ligands in alphabetical order. So that would be dichloro. Bis means 2-ethylene diamine. Bis ethylene diamine. Ethylene diamine, 2 of those. And cobalt, since it's a cation, you can say cobalt. And oxidation number 3, cobalt 3 nitrate. That's going to be the answer for that. Okay. You can see here dichloro bis ethylene diamine cobalt 3 nitrate. And then the next one, I want the pen. Give me the pen. Come on. Okay, pen. So the next one, what is the formula of hexaamine cobalt 3 tetrachloroferrate? Now ferrate comes from iron, right? It is given as ferrate, meaning it ends in 8 when you have a complex anion, right? Okay, thank you. Okay, good. So let's see how to write this formula. Okay, we're doing C, right? What is the formula of tetraamine bromochloroplatinum 4 chloride? Okay, I was reading D first. Now this one is end in platinum, so it also has a complex cation. Tetraamine bromochloroplatinum. There are 4 amine groups. 4 amine groups. Bromo, it has a bromine group, it also has a chlorine, and then the central atom is platinum. All of these are going to be in your complex ion and a chloride. Okay, now let's see. So we're going to put these in the alphabetical order. So ammonia, so first you have platinum, and there are 4 ammonia groups starting in A, 1 bromine, 1 chlorine. All of these are going to be your complex cation and then chloride. Now we need to know how many chloride atoms we need, chloride ions. To do that, we need to figure out what is the charge of our complex cation. It says platinum 4, meaning oxidation number for platinum is +4. Ammonia, oxidation number 0 because ammonia is a neutral ligand. Bromide is -1 and chloride also -1. Should give us the complex cation charge. So 4 minus 1 minus 1. So that is +2. So this part, complex cation, is +2. So then the the simple anion also need to be 2, -2. So because of that, you need 2 chlorides. Okay. Since we know what is the charge of the platinum, and there are 4 ammonia ligands, each ammonia is neutral, 1 bromide, 1 chloride, and their charges, we can find out what is the charge of the complex cation, and that also should be the same as the charge of the simple anion. So since it came to be +2, we needed 2 chloride ions. So because of that, the full complex formula would be the one that is written here with 2 chlorides. Okay. Okay, so the next one, D. What is the formula of hexaamine cobalt 3 tetrachloroferrate? Now this one is ferrate ending in 8, so that means it has a complex anion. Okay. Complex anion. Also we have hexaamine cobalt 3 as our cation. It also has a complex cation, hexaamine cobalt 3. So hexaamine means there are 6 ammonia groups. Hexaamine cobalt. That's going to be your complex cation. And then for your anion, it would be tetrachloroferrate. Ion tetrachloro, Fe, tetra means 4, Cl4. FeCl4. Now we need to figure out what are the charges that we need to put. Okay, so the charge here, we don't know the charge of the cobalt. So ammonia going to be neutral. From FeCl4, so the cobalt, hexaamine cobalt 3. Okay, cobalt is plus 3 given to us. Cobalt is plus 3. And then the ion tetrachloroferrate 3. So this is also plus 3. Right, so this is plus 3 and there are 4 chlorides, meaning negative 4. So the charge of the complex anion is therefore negative 1. And charge of the complex cation, cobalt is plus 3 because it's given here. And ammonia is a neutral ligand. So that will give us charge of the complex cation is plus 3. Charge of the complex anion is negative 1. So we want to balance the both charges. So because of that, we need 3 of these. So the complex would be therefore cobalt, ammonia 6 and FeCl4 3. That would be the answer. Cobalt 6, ammonia, FeCl4 3. You can also see the explanation for what we just now did over here in D. Okay. Right. So that's how you would name coordination compounds. Constitutional isomers of coordination compounds. Compounds with the same formula but with the atoms connected differently are constitutional isomers. Coordination isomers occur when the composition of the complex ion but not the compound is different. This can occur by the exchange of a ligand and a counter ion or by the exchange of ligands. So there are 2 types of isomers, constitutional isomers and coordination isomers. Constitutional isomers compound with the same formula but with the atoms connected differently. In coordination isomers, it occurs when the composition of the complex ion but not the compound is different. This can occur by the exchange of a ligand and a counter ion or by the exchange of ligands. And there is another type that is called linkage isomers. That occurs when the composition of the complex ion is the same but the ligand donor atom is different. Linkage isomers. I will show you an example. Some ligands can bind to the metal through either of 2 donor atoms. Okay. Here's an example of a pair of linkage or constitutional isomers. Here you can see a central atom and then there are 1, 2, 3, 4, 5 ammonia groups. And there is a 1 NO2. Here this blue atom is a nitrogen and these are your oxygen. So the nitrogen in NO2, nitrogen is the donor atom to cobalt in this formula. And similarly, in this isomer, you have cobalt, 5 amine groups, and now the connection is different. Instead of connecting through nitrogen, here connect through oxygen, ONO. You see here, this is oxygen, nitrogen, oxygen. This one, oxygen, nitrogen, oxygen. So the connection to the central atom is through oxygen. So we call these as linkage isomers. Okay, so there you can also see the color is a little bit of different. And the nitride ion can bind either through the nitrogen atom or either one of the oxygen atoms. So they are called linkage constitutional isomers. And here are some examples that can participate in linkage isomerism. Examples of ligands that have more than one donor atom are the cyanate ion. This is a cyanate ion, oxygen, carbon, nitrogen. There are 2 sites that it can coordinate to the central atom, one at a time. Both of these cannot bind at the same time. Which can attach via the oxygen atom, cyanato, NCO, or the nitrogen atom, isocyanato. Okay. And the thiocyanate ion, this is the thiocyanate ion, which can attack via the sulfur atom, thiocyanato, or the nitrogen atom, isothiocyanato. Stereoisomers of coordination compounds. Stereoisomers are compounds that have the same atomic connections but different spatial arrangements of their atoms. Geometric cis or trans isomers occur when atoms or groups can either be arranged on the same side or on opposite sides of the compound relative to the central metal ion. And then we have optical isomers, we call them as enantiomers. They are non-superimposable mirror images of each other. Let me show you some examples. Geometric isomers that can be as cis-trans isomers. In this example, you have platinum as a central atom, and then you have 2 amine groups and 2 chlorine groups. 2 amine and 2 chlorine groups. So in the cis isomer, identical ligands are adjacent to each other. So this is a cis isomer. Identical ligands are next to each other. While in the trans isomer, they are across from each other. So this is the trans. It's easy to figure out, right? The cis isomer, cisplatin, is an antitumor agent, while the trans isomer has no antitumor effect. And then we can have geometric cis-trans isomerism with 6 ligands. So in this case, you can see the cobalt is a central atom. There are 4 amine groups and 2 chloro groups. So the green ones are the chlorides and these blue ones are the amine groups. So this one you can see the same ligands are next to each other. So this is a cis isomer, whereas here they are opposite to each other. So that is a trans isomer. Okay. Draw stereoisomers for the following and state the type of isomerism. Platinum with 2 amine groups and 2 bromine groups, and they are square planar. We can determine the geometry around each metal ion and the nature of the ligands. If there are different ligands that can be placed in different positions relative to each other, geometric or cis-trans isomerism occurs. So here we can see the trans isomer, they are in opposite side, and then the cis isomer, they are close to each other. So they are geometric cis-trans isomers. The colors of transition metal complexes. The color of a coordination compound is determined by the crystal field splitting energy of its complex ion. For a given ligand, the color depends on also the oxidation state of the metal ion. For a given metal ion, the color also depends on the ligand. So there are some factors that affect the color of the ligand. Okay. That is due to crystal field splitting energy, also due to the oxidation state, and also what are the kinds of ligands surrounding the central metal atom. Effects of oxidation state and ligand on color. A change in oxidation state causes a change in color. So both of these are vanadium compounds. Here the vanadium oxidation number is +2, and here the vanadium oxidation number is +3. So when the oxidation number changes, the color changes. And these are two chromium complexes. Chromium oxidation number 3, chromium oxidation number 2. So the 3 is yellow in color, 2 is kind of maroon in color. Okay. Change in oxidation state causes change in color. Substitution of ammonia ligand. Here the substitution is just the ammonia ligand. With a chloride ligand affects the color of the complex ion. So there are 6 ammonia, here 5, exchanging 1 ammonia with chlorine. Change the color. Okay. So that concludes our session on coordination compounds.